Last time we did the product rule and the quotient rule, which are super important. You're going to do those all the time as we go on. There's another rule, like named rule for the derivative, that's called the chain rule, and we're going to do at least some of that today. But before that, I wanted to talk about the derivatives of the trig functions. Derivatives of the trig functions. It turns out there are nice formulas for the derivative of sine and cosine and all the other ones, although the other ones are less nice than sine and cosine. So let's talk principally about sine and cosine, but we'll get to the other ones too. Derivative of sine and cosine, all right? I thought just kind of like as a little warm-up, let's try to think about the derivative of sine. I'm going to try and do this by just looking at the graph. This will be somewhat informal, but this is the graph of sine of x, right? I'm going to do that thing that you did on the homework problems, which is like you look at a graph and try to draw a graph of the derivative. So this is sine of x. I would like to, let's draw the derivative of sine of x, right? I'm going to draw it just right beneath, as I usually do. I find it easiest to do it that way. And we should begin by looking at that curve and identifying where the derivatives are zero as you look across the curve. And this, of course, would be like at the top of the hill there, and also at the bottom of the ditch, the bottom of the pit. So like these points here are where the derivatives are zero, right? And maybe I'll just mark off some of these. This is pi, 2 pi, 3 pi. I'm using radians, of course. That's the kind of guy I am. That's an alpha move, using radians. All right? I'm all about alpha moves. I'm sure you can tell that about me. So those are the 0 points I marked with the big dots. And now I'm going to graph the derivative. So first of all, the derivative goes through 0 at those big dots, right? Where those dots are where the derivative graph is going to cross the x-axis. They are sort of, if I'm doing this properly, it should be right like in the middle of each of those little intervals. And then where's the curve going to go? You know, sort of, I'm going to try and connect the dots here, and you have, as usual, sort of two choices. Like between these two leftmost dots, I could go sort of up like that or down like that. Anyone have an opinion? Which one should it be? The uppy or the downy? Yeah, it's the up one. Why did you say that? All right. Any other reason? You should be able to figure that out by looking at the graph here. The slope of this graph in this region is positive, right? Because it's going up on that region, which means what I draw down here should be positive. That is to say, it should be up here rather than down here. So this part of the curve should be up there. The next part should be down here, because on this region, this curve is going down. The slope of this is negative, which means what I draw here should be on the bottom. So it's going to look like this if you do it correctly. All right? This really should go kind of up, back up like that. All right, this is what the derivative of sine looks like on a graph. And I would ask you, does that look like anything? He already said it. He blew my big surprise, the spoiler. This looks like cosine, doesn't it? So it looks like, I'm going to say, looks like derivative of sine x equals cosine x. Isn't that great? I mean, that would be great if it was true. Now, this, I would say this shouldn't actually be very convincing to you. I mean, all that we've demonstrated is like the derivative of sine x is a graph which kind of looks like cosine x. But are you really sure that that is cosine x there? I would say the only sensible answer is no, I'm not really sure. I mean, that graph down here, for one thing, you have no idea really how tall it is, right? Now, cosine goes up to 1 at that point on the y-axis. But this graph, where does it go up to? Well, it goes up to whatever the slope right there is. In my opinion, there is still a little bit of work to do to actually demonstrate that the derivative really is cosine. Whatever it is, it looks kind of like cosine. It turns out it really is cosine, but I want to do a little bit more work here. So let's actually demonstrate that the derivative here really is cosine of x, all right? It is. This is not an elaborate prank. The derivative of sine really is cosine, but there's some work to do. I mean, this is an informal thing to just kind of get us going, but we haven't really demonstrated it. Let's really do this. So, in order to demonstrate a derivative that you've never, we've never talked about the derivative of sine before. Really, the only place to go, you have to start with the definition of the derivative, which is using that limit. So, we really have to just begin like this. Lim h goes to 0. This thing which I keep on saying we're never going to do anymore, but somehow I end up doing it every time anyway. We're just doing there's a few little specific examples that we have to use a definition for. But eventually we're going to get to a point where we really don't ever need to use this anymore. What's it going to be? I got to do the f of x plus h thing, minus f of x, right? We begin with f of x plus h. In this case, looks like sine of x plus h. And then minus f of x is just sine of x, and then divided by h. All right. What can we do with this? I'm going to try and simplify things, whatever, and hopefully eventually end up with cosine. That's the idea. Anybody got any tricks to do here? What is there anything we can do with this stuff here? You can do what? I'm not sure we can easily take out the sine somehow. We have sine of this and also sine of this. It's not allowed to just put one sine on the outside of all of that stuff. That's not. Anybody want to say sine of x plus h? Is that the same as sine of x plus sine of h? And then we can cancel the... they're all... the answer is no. That is not the same as sine of x plus sine of h. Yeah. This is an interesting idea, which turns out not to do anything. You could try multiplying by that same thing, but with a plus instead of a minus, and then do some weird FOIL. It's not a terrible idea, although in this case it doesn't do much. I'm actually going to pull out an obscure fact that I wouldn't expect any of you to remember, but there is a rule about sine of x plus h. So let me just say sine of x plus h is not sine x plus sine h. All right. If it were, then you could get something going with that. But these are not equal. There is a rule though for sine of two things. Like there is such a formula as this. Anybody seen this before? If you learned a lot of fancy trigonometry, you may have learned this formula in high school. Like I said, I don't expect people to know this, but this is a somewhat obscure formula about the sine. It's this. I know I learned these formulas when I was in high school, and I was not in any kind of fancy, big shot math classes in high school. I wasn't really good at math until I got to college. Anyway, this is a true formula about the sine. I don't know if that looks familiar to you. It's fine if it doesn't. And like I said, I won't expect you to know this formula. But just for now, this is going to be useful in terms of simplifying that thing which you can see up in the corner there. All right, so I'm going to do that formula in the box to expand sine of x plus h. So it says lim h goes to 0. Sine of x plus h, I'm going to use the formula in the box. It says sine x cosine h plus cosine x sine h. There's a nice little symmetry to that, I guess. Anyway, that came from sine of x plus h. And then it says minus sine x. So now I'm continuing up there. All of this divided by h. Right? And now, can we simplify anything in there? This one we can sort of separate out in a helpful way. So what I'm going to do is separate out this thing in the middle, cosine x sine h. I'm going to sort of bring that, just reorder the fraction so that I have that cosine x sine h all by itself on the right. And then I'm going to split it into two fractions. So it's going to say sine x cosine h minus sine x over h, and then plus the other part, cosine x sine h over h. All right? And now we can actually, out of the first fraction, we can actually factor out sine of x, because I have here two things up top and they each have a sine x on them. So this is going to say sine x times cosine h minus 1 over h, and then plus, here I'm going to factor cosine x in the second one. I'm trying to separate out the x's from the h's. Sine h over h. All right. This has all just been a bunch of sort of algebra tricks so far, and trigonometry tricks. It turns out, though, that these two, so next we have to take the limit throughout everything here as h goes to 0. This will remain, the sine x, when I take the limit, that has no h in it, so it just stays as a sine x. And similarly, the cosine x has no h in it, so it just stays as a cosine x here. The question is, these two guys, what do they look like when the h approaches 0? And these are hard limits to do just using algebra, so I thought we would just, you can always just look on a graph. If you really don't know what the limit of something is, you can graph that function and then just see, like in this case, where does it go when the h is really close to 0? All right, so that's what I'm going to do. To figure out these two limits, I'm going to graph them. I'm going to go to my grapher here. Okay, actually here, I was testing this out before. Here I have that first limit. It said, remember, cosine h minus 1 divided by h. I graphed that function. I used x instead of h because my graphing program likes me to use x when I graph things instead of h. But anyway, this thing here is that first limit, cosine h minus 1 over h. And I ask you, what value does this approach when the x is close to 0, or the h is close to 0? What do you say? 0, yeah. Near x equals 0, the y value, right in the middle there, is 0. I can't make my red dot, but I can do that. 0, right? So, that means, I lost my picture. I'm going to go back here. This right here is 0. Huh? Come on. 0, right there, all right? This is what you just saw the graph of, and we saw that near the origin, it goes to 0. So that part of it is 0. And what about the other one? Sine h over h. I'm going to graph that. In my grapher, I have to use x. So it's going to say sine x over x. That will look like, all right, get rid of that one. Come on. Sine x over x. All right. Sine x divided by x. There you go. This is a graph of sine x over x. And can you see what the limit is? As x approaches 1? 0. Sorry, I said the answer. It is 1, right? When the x, which is called h in my other page there, when we go to 0, the limit is 1. So, in conclusion, this thing is 1. Come on now. All right? Anyway, it says sine x times 0 plus cosine x times 1. That's just cosine x. This is the answer. All right? A little tricky and not, not obvious to work this out, right? We had to use this weird trig formula here, and then also these limits, which are not easy to do at the end. You just look at a graph. All right? Actually, those limits, you can prove that they are 0 and 1 using the squeeze theorem. In fact, I did an example with the squeeze theorem, which was this function. I don't know if you remember. All right, anyway, in summary, derivative of sine x equals cosine x. This is really I don't know, it looks kind of simple, but in my opinion, this is really sort of an amazing and beautiful formula. Just the fact that there is this kind of relationship between sine and cosine. What I say is amazing about this is just if you consider the history of the subject, sine and cosine were developed out of the ancient Greek geometry school, whereas the derivative came about in like the 1600s Northern Europe. These are separated by immense distance in time and also in space, invented by different people, but it turns out there is this sort of calculus relationship between sine and cosine, which Archimedes or whoever invented sine and cosine had no idea that this was true, but it turned out people discovered it was true much later. It was very interesting to me. Because people, on a certain level, you feel like, I feel like mathematics exists because mathematics is the way it is because people designed it to be that way. Like, math is invented for us to solve problems. But it turns out there are formulas that are true in mathematics that are not the result of, like, nobody wanted this to be true. People didn't invent sine and cosine so that this would be true. They invented cosine and sine for other reasons, and it turned out this was true just like for no reason or like by some kind of magic. This is a deep and profound thing to think about, which is one of the things that mathematicians appreciate about the subject. Anyway, the derivative of sine is cosine. You definitely should memorize that. We're going to use that fact all the time. What about the derivative of cosine? I don't want to go through the long-winded algebra. Let's just look at the picture and see if we can sort of guess the answer here. So I am, again, going to do it on the graph. This time I'm going to start with the graph of cosine. See if we can draw the graph of the derivative and see what it is. So cosine looks like this, right? This is the graph of cosine where pi is there, 2 pi is there, 3 pi is there, minus pi is over there. All right, and then I'm going to try, just like before, graph the derivative. And I, just like before, will identify the places where the derivative is 0 on the original graph. Those are going to be spots down here where it goes through 0. All right. So it goes through 0 at pi, 2 pi, 3 pi, also at minus pi. And then we fill in the curves. It'll be a bunch of lumps, I guess, either sticking up or sticking down. What do you think in between the first two here? Should it be the lump going up or down? The answer depends on the slope of the original graph in that area. What do you say, up or down? Shout it out. Down. I see some people pointing. Down, yeah. In this region here, the slope of the original graph goes down. The slope is negative, which means what I draw here has to be on the negative side. It's like that. And then it goes up, and then down like that. All right, this is the graph of the derivative. So this one up here is cosine x. This one down here is the derivative of cosine x. And what does that look like? Looks like derivative of cosine x is negative sine of x. Yeah, this graph looks like sine of x, but it's, upside down, right? Sine goes up from the origin. Sine of x would go up first and then down. So it's just the opposite of sine x. All right, and that actually is true. If you want, you can go through a proof of this using the same basic strategy that I did before. You'd have to know the formula for the cosine of a plus b and expand it and then cancel stuff. I don't want to get into it. All right, this is the formula for the derivative of cosine. Any questions about that? So the derivative of sine is cosine. The derivative of cosine is negative sine. And you should definitely remember those two formulas. All right. This will greatly expand the kind of bucket of functions which we know how to find the derivative of. So far it's really just been polynomials or other powers of x, and then products and quotients of those things. But now we can add in sines and cosines to the mix. So how about just as an example, can we do what's the derivative of x squared plus sine x plus x times cosine x plus sine x over x to the 4? Here's a little summary of a bunch of different stuff that we've talked about over the past few days. These are all added together, so you can just go down the list here and do the derivative of each one. Somebody want to shout it out? What's the derivative of x squared? 2x. Yeah, that's the easy one. All right, next, the derivative of sine x. Cosine, that's also the easy one. That's just, I just told you that. Okay, the next one, x times cosine x. Anyone want to give me a strategy? How do you handle that? Should I just take the derivative of x and then also the derivative of cosine x? It is a product. Yeah, we got rules for that. This is a product. X times cosine x means you got to do the product rule. This is what we talked about last time. I hope you remember the product rule. This is the product rule. Remember the product rule? It's the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. So this is going to be kind of bigger than the other parts. It's the first thing, which is x, times derivative of the second thing will be negative sine x plus the second thing, which is cosine x, times the derivative of the first thing, which is just 1, right? Derivative of x is 1. All right, that's the product rule. I did the product rule with one of them was a cosine. All right? I hope you got that. And then how should I handle the last one? The quotient rule. Yeah, the last one is a quotient. And so when I take the derivative of that part, I'm going to use the quotient rule. And I hope you remember the quotient rule. Have you ever written down somewhere, if not already memorized? It's the bottom times derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. I hope I said that right. It's the bottom, which is x to the 4, times the derivative of the top, which is cosine x, minus the top, sine x, times derivative of the bottom. What's the derivative of the bottom? Yeah, 4x cubed. Great. And then divided by the bottom squared, x to the 4 to the squared. Also known as x to the 8. You would multiply those if you really wanted to. Although I don't really care about rewriting this anymore, but that's what the derivative is. Any questions about that? That was meant to be sort of a summary example of a bunch of stuff that we've been talking about lately. All right. Excellent. So we know sine and cosine. Let's talk about those other ones. Those other trig functions. You know, there's tangent, which is the most important of those other ones. And then there's all those the other ones, which are less important but still worth talking about, at least briefly. Let's talk about tangent. So let me say these can all be done as quotients. So, for example, derivative of tan x is, I'm going to, before I take the derivative, I'm going to rewrite the tan as a quotient. Anyone remember, how do you write tan as a quotient of something? Anyone remember your, yeah? Yeah, tan is sine over cosine. So this is sine x divided by cosine x. And now, you take the derivative with the quotient rule, right? So you don't actually need to do some limit definition with the tangent. Since we already know the derivatives of sine and cosine, we can just do the quotient rule. I say it is the bottom times derivative of the top, so that's cosine x times derivative of the top would also be cosine x, and then minus the top times derivative of the bottom, so the top is sine x, the derivative of the bottom, derivative of cosine is negative sine x. All of this divided by the bottom squared. This would be cosine x squared, like that. All right? And that is the derivative of tangent. Now, this actually can be simplified if you want to, and there's a nicer form of this. Anybody have an idea what we could simplify? So one simple thing is I have a minus sign and another minus sign. Those can just be written sort of together. And I'm going to write this as cosine of x squared plus sine of x squared, right? That's what the top is, over cosine of x squared. Anything we can do with that? Yeah? Yeah, the top is 1. So this is the most important, maybe the only important formula from trigonometry that I hope that everybody knows, and that is that sine squared plus cosine squared equals 1. So the top adds up to 1. What? I wrote d dx again, sorry. This should not be written. This is the kind of thing I complain about all the time. I'm going to, just because I feel so strongly, I'm going to scribble it. I already did the derivative, right? I wrote derivative here because because I'm trying to take the derivative of tangent. Now I wrote it again here because I didn't do the derivative yet. At this step, I did do the derivative, so I didn't write it again. And I wrote it again. I shouldn't have. Anyway, it's going to be 1 up top. 1 over cosine of x squared. That's simpler. This formula, so this is quite simple, although this formula is typically written as secant of x squared. Remember, secant is 1 over cosine, and so when I see 1 over cosine squared, that's the same as secant squared. And this, for strange historical reasons, is often written that way. So this is how, like if you look up this formula in a book, that's what you'll see. The derivative of tan x is secant squared of x. All right. This, you can use the quotient rule to derive that formula. All right. I got one like this for you to try. That's the derivative of tan x. How about you derive the derivative of cotan x? All right. See if you can do it. You start by writing cotan as a fraction, as a quotient of sines and cosines, and then do the quotient rule and see if you can simplify the end. This one, I'll tell you the answer, just so that you'll see if you get it right. It turns out the answer is negative cosecant squared. See what you think. I'll give you a moment. Would you like me to close the doors? Those ladies seem to have let down. I hope that wasn't bothering me. It wasn't bothering me. I don't mind hearing a lady. I hear them all the time at home, you know what I'm saying? Sounds like I'm complaining about my wife, but I'm not. That's why it's fun. My wife's great. You do it. This is how you start if you're totally stumped. The cotangent is cosine over sine. And then do the quotient rule. Hold back up and see what I did before. You could more or less copy what I did before. Zoom it out. All right, looks like people can hear. Let's chat about it. So yeah, you basically want to do what same steps like I did before. I do the derivative of cosine over sine. So the quotient rule. It'll say the bottom, which is sine x, times the derivative of the top, which is minus sine x, minus the top, cosine x, times derivative of the bottom, cosine x, all over the bottom squared. Like that, right? I hope this is what you got to begin with. You can put them together as we did before. I have sine squared and also cosine squared, only this time they're both negative. So this is minus sine squared x minus cosine squared x, all this over sine squared x. Which I do next? I know some of you did it. Yeah. What'd you say? Make the numerator, yeah, the numerator is equal to -1. I would say, so the way I would think that through is maybe factor a minus sign out of the whole thing. This is equivalent to what he was going to say. Right? If I factor a minus sign out of the entire numerator, since they were both negative, it makes them both positive. And now those two things will add up to 1 in the top, just like before. So -1 over sine squared of x. All right? However you want to say it, this numerator is equal to -1. All right? And then 1 over sine is the same as cosecant, right? So when it says 1 over sine squared, that is the same as cosecant squared, and I have a minus sign there. Negative cosecant squared of x. There you go. That's how we do it. So it's just the quotient rule. You got to simplify everything correctly. Any questions about that? All right. So in this same way, you can get formulas for any of those other trig functions. And I don't want to go through all of them, but I think we should, you should have these in your notes somewhere. So I'm going to write down the whole list. So the derivative of sine is cosine. The derivative of cosine is negative sine. These, well, I'll say this in a moment. The derivative of tan x is secant squared x. The derivative of cotan x is negative cosecant squared x. And the derivative of secant x turns out to be secant x times tan x. And the derivative of cosecant, these last two, you could derive them yourself if you wanted to using the quotient rule. It's not hard. It's really very similar to what we just did. Negative cosecant x cotan x. All right, these are the derivatives of all the trig functions. Like I said, you should know that these formulas exist. I won't expect you to have them all memorized. I will expect you to have these two memorized. All right, the other ones, you may come across the other ones on your homeworks. You should see it on the homework and recognize that there is a formula and go look for the formula. On a test or a quiz, I would only expect you to know the first two. All right? I might, if I wanted to go crazy with these on a test, I might give you the rest of them so that you could use them on the test, but I won't expect you to have them memorized. All right, these are the derivatives of the other trig functions. Any thoughts about those? Great, so now we can do derivatives of any trig functions. We got 15 minutes left. I think that's enough time to start talking about the chain rule, which is our last of the major derivative rules. The chain rule, the most exciting name of all of them. The product rule and the quotient rule are for products and quotients. The chain rule is for chains. I'm not completely sure why it's called the chain rule, actually. It's about compositions of functions. So the chain rule, this is about the derivative of one function plugged inside of another function. This is called a composition of functions. F of g of x, one thing inside of the other. How do you take the derivative of such a thing? All right? I don't know if this looks totally weird. I mean, we're going to talk about it. There is a formula for that. It's called the chain rule, right? So you would use this in situations like the derivative of sine of x squared plus 5x, right? I know what the derivative of sine is, and I also know what the derivative of x squared plus 5x is, but how do I take the derivative of the one thing inside of the other thing? And the answer is you use the chain rule, and it's a fairly workable formula. If you know the derivative of the outside part, and you also know the derivative of the inside part, you just combine them in a certain way according to the formula. All right, or something like this. How about x to the 7 plus 4x all to the 10 power, right? This one looks a little different because you don't have, like here I think it's clear, like I have this function which comes first and then this other function which is inside of it. Here you have, it's still a thing inside of another thing, but actually the inside is sort of written first and then the outside is over here, right? So in this case we have this polynomial which is stuck inside of a 10th power, all right? The moral of the story is what's important in the chain rule is the function on the inside versus the function on the outside. And it's not always the case that the outside function is written first. Here it is, the outside is sine, and that is written first. But here the outside function is the 10th power, even though it's written sort of at the end, just because of the way we write exponents on the right side. All right? Anyway, these are the situations in which you would want to use the chain rule. And the chain rule comes up all the time in the real world. It's useful whenever, the derivative is useful when you want to see how something is changing. The chain rule in the real world would come up if I am trying to measure something, the change of something, but that thing that I'm measuring is also depending on another something. It's kind of like, from day to day, like airline prices will change because the airlines have to change their prices for whatever reason. But a lot of what the reason the airlines are changing their prices is due to a lot of other factors, including things like the price of oil or the price of fuel. So if you want to really analyze how the airline prices are changing, at some level you have to break into an analysis of how the fuel prices are changing. This is a classic kind of situation of one thing is changing, which is depending on something else which is changing. And in all kinds of situations like that, you use the chain rule to deal with the one thing which depends on the other thing. A thing inside of another thing. All right? Anyway, let me tell you the vague idea here of the chain rule. As usual, when you don't have anything to go on for a formula like this, you have to break out the definition of the derivative. And this very well might be the last time we really use this. Don't take my word for it, but if you really have nowhere else to go, how do you find the derivative of this? I'm just going to say this is the vague idea. Actually, what I'm about to do is not fully a fully rigorous proof of the chain rule. The chain rule actually is quite difficult to prove in complete detail, and I believe that our textbook doesn't even do it. They say we don't want to do it because it's too hard. But here's the basic idea of it, and I will point out what you'll be able to tell the step at which this isn't totally technically accurate. So I am doing the definition of the derivative one last time, like so, right? The derivative of f of g of x, you do the lim h goes to 0, where first I plug in x plus h instead of x, and then I just use the original function like it is. All right, and here's the trick. This involves just a simple trick like usual when I'm doing these formulas. The trick this time is about multiplying and dividing by the same thing. So I'm going to do this. This is the same as f of g of x plus h minus f of g of x. I'm going to divide on the bottom here by g of x plus h minus g of x. And times g of x plus h, minus g of x divided by h. All right, so I took, this numerator and denominator and sort of split them apart like that and stuck this other thing in between. But it's still equal, because this thing that I introduced here would cancel out and you just get the thing up there. But anyway, if you look at the two parts of this thing, if you take the limit of each part as h goes to 0, can anybody tell me what is this second part if you take the limit as h goes to 0? This part? Yeah? No, it's not 0. Okay. Yeah, what happens? I have to take the limit of this whole thing as h goes to 0. This is a kind of complicated thing, although this looks familiar to me. Yeah? It is the derivative of g, right? That's the definition of what the derivative of g of x would be. So this part becomes g prime of x. This is actually the last step in this little derivation. Here's the sort of hazy part. This part, it turns out, and this is really the hard step of the proof, which I'm not going to get into. This part is that. It is f prime of g of x. When you look at this, what you have on the inside here, I have the g of x plus h and the g of x here, divided by the g of x plus h minus the g of x here. It turns out this setup here has the same basic effect as if I just had x plus h and x over h, and it makes a derivative of f, all right? But it's f which has g plugged into it, right? This thing is definitely not just the derivative of f, because it's got all those g's in it. It turns out this is something like a derivative of f, but it has g of x plugged inside of it. And anyway, this is the chain rule. So I'm going to write this again more nicely. The derivative of f of g of x is f prime of g of x times g prime of x. And this you should also memorize. This is the last of our big derivative formulas. And this is the chain rule. All right. And just like the product rule and the quotient rule, I don't actually, I know the chain rule, but I don't really memorize it in terms of a formula that looks like that. I think of it in my head as sort of a slogan in terms of the outside function and the inside function. So in this example, or not an example, the way it's written here, I think of the f as the outside and the g as the inside, right? And then what I see on the right here as a slogan, so this is how I remember the chain rule. Somebody asked me, what's the chain rule say? What I see here is the derivative of the outside with the same inside. That's this, right? F prime of g of x. It means I take the derivative on the outside function, but I leave the inside the same as it is. And then times g prime of x, that's the derivative of the inside function. So it's the derivative of the outside with the same inside times the derivative of the inside. This is how I remember the chain rule in my head. Sometimes you will confuse yourself if you try to write out the formula like that with the f's and the g's. I would suggest you try to remember just sort of in words the idea of the chain rule. The derivative of the outside keeping the same thing on the inside, and then separately times the derivative of the inside. We got 5 minutes. I think we can do a few examples. It's not so hard. All right, derivative of... let's do this. I think this is what I wrote before. Sine of x squared plus 5x. All right, you got to look at that and ask yourself, first of all, what rule am I going to use? Should it be the product rule, the quotient rule, the chain rule? It's not the quotient rule. I don't see any quotient there at all. It's also not the product rule. Don't get confused. You might say, isn't this like sine times that other thing? Isn't that a product? No, it's not a product. It's not sine times that other thing. Sine is a function, and it's that other thing stuck inside of the sine function. So it's not a product rule. It is a chain rule. Anyway, the sine is the outside, and then this polynomial here is the inside, right? And so the chain rule says, I scrolled it away, the derivative of the outside with the same thing on the inside. So I'm going to take the derivative of the sine, it becomes cosine, with the same thing on the inside. That's the first part of the chain rule, right? The derivative of the outside with the same thing on the inside. And then times the derivative of the inside. And in this example, that would be 2x plus 5. That's how we do the chain rule. You take the derivative of the outside, keeping the same thing on the inside, and then times the derivative of the inside. All right? Don't get too eager with the derivative. Sometimes people want to go sort of go ham on this and just take the derivatives everywhere. It's a common mistake to just go straight to, I do cosine, and then I do 2x plus 5. Take the derivative on the outside and also the derivative on the inside. This is not correct. What is correct is what I said before. You have to do them separately. The derivative of the outside first, same thing on the inside, and then the derivative of the inside. All right, don't do that. Let's just do that other example that I wrote at the beginning. Derivative of x to the 7 plus 4x to the power 10. All right. Again, this is a chain rule because I have a thing on the inside and another thing on the outside. Right? It might be a good idea to just, even in your head, identify for yourself what is the inside and what is the outside here. Well, the inside is the x to the 7 plus 4x, right? And then the outside is the 10th power, right? Like I said before, sometimes the outer function is actually written on the end. In this case, it is. Anyway, I'm going to do the same old chain rule, the derivative of the outside using the same thing on the inside. So when I take the derivative of the outside, I do the thing with the power. The power rule means the 10 comes down to the front and then decreases to a 9. And I keep the same thing on the inside. So it's 10, x to the 7 plus 4x to the 9. All right? This is taking the derivative of the outer thing, leaving the same thing on the inside, and then times derivative of the inside, 7x to the 6 plus 4. That's how we do chain rule. All right? Make sure you have all those parentheses. They matter. If you left out actually any of those, it would change what it means. All right? I think that'll do. More on this next time.